Take it away.
Okay, great. Okay, I'll guess that's 10. For now, I might regret the decision later. Okay. So this is a continuation of the last talk on the recent developments on the black hole information problem. I guess you can kind of see me. That's over. And so this slide we already went past last time, but sorry, Martin, do you mind if I just minimize this? Great. We went over this last time, but I'll just remind you. So this is the computation of the page curve, which tracks the behavior of the von Neumann entropy of the Hawking radiation, not using the standard effective field theory formula of minus trace rho log rho, but instead using quantum extremal surfaces I, which behave very differently. So initially, we have a quantum extremal surface, which is the empty set. And so the von Neumann entropy is just computed by the generalized entropy of chi, when this is the empty set, is the von Neumann entropy of a complete spatial slice. So that's just like the Hawking calculation. But at the page time, meaning about halfway through the evaporation process, a new quantum extremal surface begins to dominate, meaning it has a smaller generalized entropy, which I'll remind you is the sum of the area of 4 Planck units plus the von Neumann entropy. That has a smaller generalized entropy than the empty set. And indeed, what we begin to see is that the entropy starts to decrease. So this is at a single moment in time, and this is that moment of time illustrated here. So you'll notice this quantum extremal surface sits just a little bit behind the event horizon. It's not actually at the event horizon, just a few Planck lengths behind it. All right, so that's a recap of last time.
Quick question.
Yes.
In the course of evaporation, etc., what happens to this extremal surface? What is it?
Good. So it moves. So this is the quantum extremal surface for this moment in time. If you think of the moment in time as determined by the asymptotic boundary. So this is the quantum extremal surface for where this spatial slice hits the asymptotic boundary. And if you move up to the next one, you can ask where is the quantum extremal surface. So that's what I drew up over here on Monday. As you move up, the quantum extremal surface moves in a space-like direction. So it moves. It's almost null.
This diagram is not the diagram I want, right? Because I want an evaporating one.
This is an evaporating one. Just ignore what happens up here.
Okay. Well then, yeah. So.
So it just moves in a space-like direction.
No. But the what I'm saying is it's got to leave the event horizon. If you're drawing it, if it moves up to scry,
it's not going to leave the event horizon until we lose semi-classical control. So as long as it begins to
yeah. But there's a point where it, like you're in your diagram. There's a point where it crosses the diagonal line.
You mean this line?
Yeah.
It never crosses this line. It moves in a space-like direction progressively closer to null.
So what's the orange line dotting?
The orange line tells you which time slice this is computing the entropy on.
Ah, okay.
Yeah. So the orange slice.
So there's two orange lines.
That's the blue slice over
there. Sure. Okay.
Yeah.
Thank you.
Yeah.
So it's just inside the event horizon for the whole time.
That's right.
And then.
Well, okay. The whole time while we have semi-classical control.
Right. Then something happens, quantum gravity, whatever. What happens? Does it appear later on above?
You mean after the evaporation is over?
After the evaporation.
We do not. We because we want to stay in the region of semi-classical control. We do not purport to know what happens.
Right. You're agnostic about.
Yeah, we're completely agnostic about that. Yeah.
Got it.
We're sticking within the regime of the paradox, which is where semi-classical effective field theory is valid, but the naive results you get from it are very different.
Got it.
Yeah.
Thanks.
So, but do you know when it breaks down?
Sure. I mean, we do.
Of course, at the very end of the operation, sure, but.
I mean, we know when semi-classical effective field theory breaks down, which is effectively when the curvatures become comparable to other scales of the problem. So that's when we don't have a perturbative expansion is not valid anymore.
Okay.
Yeah. So effectively, you do a perturbative expansion in GH bar, and when you find that as you add more terms, the first image is asymptotic series, so eventually they'll start to blow up, or they'll start to diverge from the value you expect. But if the first couple of terms also are getting progressively larger, then you know that you're way out of the regime of validity.
Okay.
When you say curvature scales are, when you answered Ulysses' question, how exactly are you measuring curvature in the geometry that's evolving? Do you have some kind of model of how big the mass is as the evolution
We're talking about the
progresses?
Kretschmann scalar at the event horizon.
Right, but the Kretschmann scalar is so in order for you to compute the Kretschmann scalar, you need to have a metric.
Sure.
So what do you know what the metric is?
So we're solving the. So again, this is the regime where we can do this calculation exactly is two-dimensional dilettante gravity. The equations are linear. We can solve for the equations. The point is with the stress tensor. So we have the equations for the dilettante in terms of the stress tensor. Okay, so we can actually we can solve this exactly. Now the problem becomes when we start seeing the I mean dilettante gravity is special. The problem happens when we start seeing the large derivatives of the dilettante of the event horizon. When the stress tensor wants to source that.
Like if I'm thinking of a Schwarzschild black hole that's evaporating, to some degree of approximation, I could just take m, the parameter that appears in the metric, to be like some function of time, say.
Sure.
And are you saying that, like, suppose I want to compute maybe Kretschmann, maybe some other thing, using that metric, but m is now a function of t. I can redo the whole calculation, and then I will get some dependence on m of t.
Yes.
And then when you're saying like when m of t becomes of a certain size, namely when it's sufficiently small.
No, that's not quite. I mean, you could do it that way. You could say when m of t is really small, but the way we actually like to do it is we look at the behavior of the stress tensor of the quantum fields. If the stress tensor of the quantum fields is starting to have a large effect, if it is getting bigger and bigger, and it's starting to have a large effect on the geometry, then we know we're leaving the regime of effective field theory. This is a very standard effective field theory, right? You look to see what the stress tensor of the quantum fields is looking like. And as long as you're working perturbatively and it's valid, then everything should be small. But if your stress tensor is getting bigger, then you're starting to have a problem.
Right, and the stress tensor here is some expectation value of the stress tensor with some fields in the background being some being some state that you've like a reasonable state you've selected, maybe some kind of like.
So I mean, we start out before we couple these two. We start out in the thermal state. For example, we could start with a pure state if we wanted to. And this state is this is the vacuum. And so we can actually compute exactly everything. I mean, we're not picking out the state. We're imagining, suppose you take Schwarzschild in a Hawkings state, then you say, okay, I prepared this state with the Hawkings state in Schwarzschild, and then I couple it to a CFT in the ground state.
Okay.
Then we know what these two states are.
This is all like old EFT black hole evaporation description. Okay.
Okay, so this is the slide we ended with last time. So what do we have? We have two calculations of the entropy of Hawking radiation of ADS black holes. We have Hawking's original calculation adapted to the ADS. And again, as I mentioned, you can do this. You can check and make sure if this is exactly the same as Hawking's original calculation. The follow-ups don't make a big difference. The calculation is effectively minus trace rho log rho. I mean, Hawking's calculation is a little bit more general than that, but that is effectively what it is. And this increases to the thermal value, which is where the von Neumann entropy is maximized. Our calculation with quantum extremal surfaces, alternative calculation, not minus trace rho log rho. And that instead gives exactly what Page predicted, which is a decreasing entropy after the Page curve, after the Page time, rather than entropy that just kind of plateaus at the thermal value. Now, the surprising thing is that both of these calculations don't require access to an analysis from quantum gravity. Both of these use things like areas and effective field theory, semi-classical fields called quantum fields propagating on a curved space-time, minimal back reaction, and so on. So both of them can be done with the tools of semi-classical effective field theory, but of course, they give very different answers. Now, this is something that I'm going to talk a lot about momentarily, which is the question of what is semi-classical approximation then? Why is the naive semi-classical approximation giving us minus trace rho log rho, but there's this sort of backdoor of quantum extremal surfaces where we can, if we're just kind of given what's called in quantum computation oracle knowledge, where we're told, okay, this is the right way to compute this, then we don't need to know the details of the black box of how to go from, quantum gravity, the state, to actually computing the minus trace rho quantum gravity log rho quantum gravity. we can just say, okay, we have this oracle access, oracle knowledge. The right answer is given by quantum extremal surfaces, and then we can actually compute that without knowing the details of the circuit that actually gives us the quantum extremal surface answer. So and I'll talk a little bit more about quantum hard tasks and so on, what the relevance is here. But there's a suggestion, which I'll justify shortly, that there are the rules for computing quantum hard tasks, and computing with limit entropy is what's called a quantum hard task. It takes an exponential amount of time to compute it. That is different for quantum and classical gravity. So I'll say a lot more about this and justify it momentarily, but first let's ask the following question. Why does quantum gravity repackage entropy in terms of quantum extremal surfaces? Why not minus trace rho log rho? So this is sort of trying to get at understanding what's the difference between these calculations. So I'll talk a little bit about the justification for quantum extremal surfaces in that formula. So the golden standard for deriving things from quantum gravity in semi-classical gravity is the gravitational path integral. So the question is, the natural question is, can we derive the quantum extremal surface from a semi-classical saddle point approximation to the gravitational path integral, which effectively computes the partition function of quantum gravity? So the partition function is given by, this is the gravitational path integral. This is an integral over all metrics with a given set of boundary conditions. These are not just on-shell metrics, meaning these are not just metrics that solve the equations of motion. This includes metrics that don't solve the equations of motion. We're integrating over all of them. And I think we're integrating is e to the s grav, where this is the Euclidean action, Euclidean gravity action. Now, this is a very ill-defined thing. And it's even worse than the quantum field theory path integral, which is already pretty ill-defined. But somehow it's really good at giving us the right answer. As physicists, we say, okay, well, let's use it. Let's see what happens. Now, typically we're not able to do the path integral over all metrics. The one exception is brilliant recent work out of Stanford on doing this type of thing in two-dimensional gravity, where you can actually do this exactly, which is kind of miraculous. It uses the groundbreaking work of Miriam Mirzakhani, the Mirzakhani recursion relations and so on. So, is
there a topology being relevant here?
That's a good question. We typically don't constrain the topology, although there are arguments in favor and arguments against that. Typically, we say all we do are boundary conditions here. We just impose boundary conditions, and we don't care about which topology fills them in. So, in fact, shortly you'll see there's a very important topology difference between two saddles that we'll be comparing. So we typically don't demand a particular topology.
And what do you mean by the recent stuff, 2 dimensions, that calculates this exactly or something?
So there is a non-perturbative calculation that exactly computes the partition function of quantum gravity in 2 dimensions.
But is this, the ill-definedness of the comments that you made earlier about this being ill-defined?
Not in 2 dimensions, good.
So
not in 2-dimensional dilettante gravity. So that is one case where we can make things precise. 2-dimensional dilettante quantum gravity can be solved exactly.
So does that mean that the QFT can be solved exactly as well? The QFT?
No, good. That's in pure gravity, pure 2D dilettante gravity, no quantum fields. In that, if you want to add quantum fields, then you're already in a very different regime.
Is this a Euclidean thing then?
This is Euclidean, yes.
So it's like e to the minus s, where s is the action for dilettante gravity, which is
for Euclidean dilettante gravity.
Euclidean dilettante gravity, and then the integral over all metrics is all metrics on surfaces.
Yeah, so we're basically including arbitrarily many handles, arbitrary genus. Yeah.
And then well-known results for the moduli space of such metrics in 2D. There's loads of results. Mathematically, it's been studied for decades.
That's right. So basically, they use the Mirzakhani relation to do this calculation.
Mirzakhani relation. What do you mean?
The
exactly?
recursion relation that relates the volumes of the handle bodies to one another. So she computed them. She gives beautiful recursion relation. They actually were able to do this integral exactly.
Great. That's really cool.
Yeah, it's pretty tremendous work. Checker in Stanford. Okay, so typically though we don't deal with this whole thing.
The pure to the
Dilettante
gravity, just because that's the one case where things can be solved exactly, or is there a physical justification
So,
over and
good,
above? That's
yeah.
the case where we can calculate things.
There are multiple reasons. Now, 2D dilaton gravity things can be done computed exactly, but also 2D dilaton gravity, once you add matter fields, can be obtained as a dimensional reduction of four-dimensional gravity, a certain sector of four-dimensional gravity.
Spherical symmetry.
Spherical symmetry, that's right, with certain matter fields. So there is a sense in which it's physical. In particular, if you're working with 2D dilaton gravity coupled to conformal matter, to a conformal field theory, that can be obtained from a four-dimensional charged spherical symmetric black hole, charged black hole, yeah, magnetically charged. Okay, so typically we don't do this whole thing, but we can do a saddle point approximation if we're working semi-classically. We say, all right, let's do a semi-classical, let's do a saddle point approximation where our small parameter is g Newton times h bar. Now, when you do this, and I'll go into a little bit more detail momentarily, but just the sort of top-down perspective, what happens is you say, okay, I'm going to do a saddle point approximation with the partition function. I'm going to use the partition function to compute the von Neumann entropy, and I'll show you in a moment how that's done. And what we find actually is there are two saddle points. One of them corresponds to Hawking's calculation, and one of them corresponds to the quantum extremal surface calculation. Now, it corresponds to Hawking's calculation in the sense that it agrees with his answer. Of course, Hawking didn't actually do this calculation in this way. He didn't use a saddle point approximation to the gravitational path integral. But that answer gives you the Hawking's result. And after the page time, that saddle that corresponds to Hawking's result becomes subdominant because the new saddle to the gravitational path integral, it has a smaller action, smaller Euclidean action. Okay, so a little bit more in detail. So how do we generally compute von Neumann entropies? We use Renyi entropies more generally. In a non-gravitational theory, there's a very standard way to do this. It's called the replica tray. So again, to remind you, the von Neumann entropy is minus trace of rho log rho, which we can rewrite, cursor, which we can rewrite in this way. Now, this is a little bit uncomfortable because first here you think of n being an integer. You introduce n copies of your system. Rho to the n is the state rho on n copies, n independent copies of your system. They're called replicas. You replicate your system n times, and then you have to just ignore the fact that n is an integer. And you say, okay, well, I'm going to analytically continue n to the reals, and then I can take a derivative with respect to n, and the limit as n goes to 1. Now, you might say this sounds really sketchy, but you can check Harleman's condition and make sure that this actually is a unique analytic continuation to n in most cases. So actually, this is at least somewhat well defined. All right, so this is how we typically compute it, not in gravity, but just in general. This is one way of computing the von Neumann entropy. All right, so now let's think about what we wanted. Suppose we want to compute, let's forget about the n goes to 1 limit. Let's just think about computing, for n equals 2 for a moment, just to get an idea of what this object is like. Okay, so in gravity, we want to compute the partition function for n equals 2. So this can be rewritten in terms of the partition function on n independent copies of the system. So if we want to do it for n equals 2, then we're computing the partition function for n equals 2. Now that means that we're going to take 2 copies of the Euclidean ADS boundary conditions at infinity. That just looks like 2 circles here. We're working again in Euclidean time, so this is the Euclidean time coordinate. All right, we take 2 independent copies, and then we ask, okay, what kind of geometry could fill in the space-time with these boundary conditions, the Euclidean geometry? And we're going to be working in a saddle point approximation, which means that we're looking for on-shell action, for on-shell solutions. We're looking for solutions to the equations of motion. Okay, so what is it? Well, it turns out there are 2. One of them is just Euclidean ADS, which just looks like a hyperbolic disk. And the other one is this very unusual Euclidean wormhole. So this is not like the Einstein-Rosen bridge in the sense that this is connected in Euclidean time, unlike the Einstein-Rosen bridge, which is just a Lorentzian bridge, which you can't travel through it in time. This is connected in Euclidean time. So for n equals 2, we have these 2 different saddles. We have one that's disconnected, and we have one that's connected. And as it turns out, if you ignore this one, which, maybe you want to, maybe you didn't know about it, maybe there are other reasons why you don't like it. We sort of, with the gravitational path integral, we kind of play fast and loose. So you say, you look at this one, you say, okay, well, this looks pretty good, let me go with that. And you end up reproducing a calculation that looks exactly like Hawkings calculation. Entropy increases and eventually saturates at the thermal value. Now, the exchange in dominance between these two happens exactly halfway through evaporation. So approximately halfway through evaporation, plus or minus correction factors. So that means that if we're really taking the saddle point approximation seriously, this is the thing that we should be computing after the page time. And indeed, this connected replica, we call it replica wormhole, this connected replica gives us the quantum extremal surface prescription. This is a way of deriving quantum extremal surface prescription from the gravitational path integral. And it does give us the page curve. So this is another way, this is one way of getting it, which is at least somewhat top down. Now, we don't know exactly what the gravitational path integral is. We don't understand it that well. That said, we do expect that it is describing to an extent a partition function in quantum gravity. So this is I wouldn't say go as far as saying a derivation. This is an argument for quantum extremal surfaces from some sense from quantum gravity. It's from the gravitational path integral.
So is the stuff you said about what happens in 2D pure gravity and how you can actually compute the gravitational path integral in that Euclidean setting? Are you using any of that here, or no? That's just something independent.
So this is, it's a two-part question. In principle, you do not have to use that to do this because this is a semi-classical approximation. We're looking for saddles. We're not looking to do the full gravitational path integral here. And that full gravitational path integral is when you're working with pure dilettante gravity, not when you have extra matter fields. That said, there actually was a group of people who did a calculation where they added a brain to 2D dilettante gravity with which had a certain class of states on this brain. And this is a very simple system. So they actually were able to add it to the 2D pure dilettante gravity action and do the whole thing non-perturbatively. So they actually were able to completely exactly compute it, and they got the same thing. So there is a setting where you can do it. It's a bit of a toy model because the brain sort of acts like a.
You mean they got the same thing, like they computed the saddles, what they got, and
no, they didn't compute the saddles. They actually summed it up exactly.
Okay.
Yeah. So in that's the one case where it's been done exactly, computed. I mean, they show that there's saddles in that case too, and then they actually did the calculation and found that the non-perturbative corrections add very little to this one. They don't modify the calculation very much. So that was a justification of this calculation.
But the final answer, what's the final answer of the calculation? It's the von Neumann entropy, right? That's what you're after.
Yeah.
Okay.
Yeah, and so the
So
page curve that they got was almost identical with like very tiny corrections to the one you get from the saddle point approximations. Okay, so the question is, so the GPI here stands for gravitational path integral. So should these topologies be included? And at first you might say, well, sure, why not? They give you the right answer. Why would we not include them? Now, if we include these topologies, we have the following property of the gravitational path integral. So P denotes the gravitational path integral. B is the boundary manifold. So B to the n here is going to be n copies of the NADS. Now, what we find is that the gravitational path integral of n copies of the boundary manifold B is not identical to the gravitational path integral on one copy raised to the power n. Right? Because if we look at this, this is two copies of the gravitational path integral. So this is PB raised to the power 2. This is PB2, close parentheses. So they look different. All right, well, why is that a problem? Okay, so if we go with the conventional wisdom that the Euclidean path integral computes the partition function, then the gravitational path integral on B is equal to or approximately equal to the partition function on gravity, these boundary conditions, which tells us just, direct logic here that the partition function of n copies of B is not the same as the partition function of B raised to the power n. Now, why am I harping on this? So the important thing here is that having these connected Euclidean wormholes gives us non-trivial correlations between these n boundaries. And that's a problem because these n boundaries are n independent copies of the system. They should not be correlated with one another. These correspond to n independent copies of a given quantum field theory, the boundary, the dual quantum field theory, as n independent copies of it. And including these connected topologies gives us correlations, even though these are n independent copies, so everything should factorize between them. The algebra of operators, everything should factorize between these quantum field theories as n independent copies of the same system. So this gives us what we want in the sense of the von Neumann entropy, the right curve for it. We can derive it from non-perturbative quantum gravity in 2 dimensions, but at the same time, it gives us something really weird, which is that these quantum field theories appear to be non-factorizing, even though they have to be factorizing. So we're still a little bit confused about this. Now, one option is that the gravitational path integral computes an ensemble average. Now you say an average over what? Well, maybe it's an average over theories with different couplings. Maybe it's an average of over different values of GH bar, maybe neighboring values of GH bar equals something small plus epsilon, and you're averaging over epsilon. Maybe you're averaging over states. Maybe they're non-perturbative corrections, e to the GH bar that restore factorization. I'm not going to go into the details of this, but there's some decent evidence in favor of this idea that if you include all non-perturbative corrections, you actually restore factorization. So
I don't understand the issue.
Yeah.
The independent thing was just a kind of heuristic way to justify the formula you wrote down to compute the von Neumann entropy.
Not at all. I mean, to compute it, we introduce n copies of a system. Now we take the limit as n goes to 1, but that limit appears to be telling us that at any value of n, which is not 1, we have n independent copies that are correlated with one another. And in particular, moreover, if you want to compute the Renyi entropies, which are effectively the von Neumann entropy, but instead of n equals 1, n equals some other integer, then we find that these n independent copies we have on physical are actually correlated with one another, which they should not be.
Well, the thing that's right, but the thing that's puzzling is that like as soon as you allow for different topologies, then like obviously you don't even need to explain the logical thing. You're obviously going to have cobordisms, and therefore you lose this independence.
Not necessarily. I mean, I could have put a handle on this that wouldn't have messed with it. So it's not that all new topologies are going to be a problem. It's
No,
just,
I didn't say all. I just said that as soon as you have boundaries and you allow for things to connect to one another, then how can they be independent?
That's right. And so for a long time, it was thought that these wormholes are just illegal and they're not allowed in quantum gravity. And now we're seeing that if we say that they're illegal and not allowed in quantum gravity, then we get the wrong answer. So they must be included, and we have to find some physics explanation for the phenomenon that they seem to induce. Yeah.
So you go back to this slide where you're using Replica to compute the von Neumann entropy.
Yeah.
So rho to the n there is an n-fold tensor product. At least it's supposed to be.
Yes, it is.
Right. Okay.
Yeah,
Right.
Exactly.
So the problem here is we're allowing entanglement in systems
That are
in some
independent.
sense.
Yeah, that's
Right.
right.
Exactly.
Yeah, we're allowing this entanglement with the system and itself, and another copy of it.
Well, that's what I mean.
Yeah,
Right? We're allowing the fictitious replicas to become entangled.
precisely.
And then entanglement is showing up as our allowance of these, right? So
Exactly,
there's
that's
something very
exactly
EPR in this. Well,
Yeah,
feels
it's-
almost like that, except these aren't standard Lorentzian wormholes.
That's right.
Yeah.
That's right. Yeah.
So I haven't worked closely with Replica in this circumstance before. Is it obvious that the replica trick here only works if we don't allow entanglement between the systems, like
So you mean
between the copies? I mean, if we generalize and replace rho to the n, which is just a factorizable n-fold tensor product, if we allow it to be a more general, potentially entangled or correlated combination, is it provable that the replica trick fails to produce the von Neumann entropy?
So I don't actually know the answer to that. If there's another way of rewriting this replica trick or modifying it a bit so that we still gives the von Neumann entropy, I don't know.
Is that my first
It
guess?
does, I mean,
right?
but in order to resolve this problem, it would still have to explain why this is wrong.
Well, I guess so. I mean,
I should say, maybe let me add.
it's just not clear that this is the unique way to do the replica trick to give you the binomial entropy.
No, the only thing we know is that this is the unique analytic continuation given this form of the.
I see.
Yeah, we do know that's a unique analytic continuation for Karlman's condition.
Right. It's unique analytic condition, and that depends on rho to the n being a factorizable and full.
Yes, exactly. Yeah. So there is some uniqueness which is known here.
That is very confusing.
It is very confusing. Now, the thing is, so of course, if you do an ensemble average, then that explains where you end up getting correlations.
Right, because if you do ensemble average, you're going to end up getting linear combinations. Over
Precisely.
different hits.
Precisely.
Right.
So then, so
Although those wouldn't necessarily be entanglement, those would be because those are all separable. They're all sums
that's
of-
right. But then rho would become, instead of being so
it would be a linear combination of n-fold tensor products, which is still separable. It's not entangled.
it would still be separable, but the rho that you're looking at may be sort of spread over many.
Right.
So
Exactly.
then it would be effectively entangled, even though each one actually isn't.
Right.
So it sort of introduces effective correlations, which are exactly what we would expect to show up here. So for a while, we thought that maybe semi-classical gravity is just an ensemble average. But the problem is when you go to higher dimensions, this works in 2D actually, we can actually show that 2D gravity is an ensemble average, which is great. But then you go to higher dimensions and then you ask, okay, what is it an average of? And Ed Witten actually had a paper just a couple of weeks ago where he argued very effectively, I would say, that in higher dimensions, it can't be an ensemble average. But he suggested that the averaging is happening over values, neighboring values of GH bar. So there is an averaging, it's an effective averaging. And the reason for that is that there's no, the large G limit of black holes doesn't exist in quantum gravity. Because the Hilbert space, every time you go, so if you say GH bar equals 10 to the 6th, sorry, 1 over 10 to the 6th, then your Hilbert space is growing sort of exponentially with inverse of that. Now you add one more, you say, okay, now GH bar equals 1 over 10 to the 6 plus 1. And most of the states in the Hilbert space are not new. So there's actually no good limit. There's no small GH bar limit to black holes in quantum gravity. It's not a well-behaved limit. So that's a very, very beautiful paper that came out of this. Okay, so, okay, so, yeah, so there are many different possibilities. This is an open question right now. What is the path integral? Really computing, is it computing an ensemble average over what? Maybe it's computing something that's an effective ensemble average. Maybe another option is just a good tool for computing something called sub-averaging quantity. So it's just like another black box. Many possible questions. And I'm going to use maybe 5 more minutes to talk about a somewhat different approach, a somewhat different question that we can ask now and we are asking now. So we have 2 ways of computing the entropy of Hawking radiation, as I mentioned earlier. Quantum extremal surface, or equivalently, we can say the gravitational path integral. Or Hawking's calculation, which is, effective field theory, Bell-Above transformations, minus trace rho log rho, effectively. So these give different answers. Now, ultimately, to resolve the black hole information problem, we need to answer the question of where these 2 approaches diverge. Why doesn't this give the same answer as that? Where does this differ from that in the same language? Right now, they're in 2 different languages. This is in the language of Bell-Above transformations. This is in the language of the gravitational path integral. So they both appear to be right, given the tools that they use, but of course they can't both be right. So where do these 2 approaches diverge? Can we put them both in the same footing? So if you asked me before these new developments on quantum extremal surfaces, where Hawking went wrong, I would have said, and I'll explain what Harlow Hayden means in a second, I would have said, oh, there's this calculation by Harlow Hayden that probably means that somehow Hawking's calculation lost track of exponentially complex data in the state. When I say exponentially, I mean exponential, essentially in GH1, in 1 over GH1. So what is the logic here, and what is this Harlow Hayden calculation I'm quoting? Well, Harlow and Hayden showed that decoding the Hawking radiation after the page time, which is when you can actually decode it, but the information starts to come out of the black hole, decoding it is exponentially hard in the log of the dimension of the Hilbert space, which is proportional to 1 over GH bar. this is known as a quantum hard task. So if you want to actually do this, you would need a quantum computer that had exponentially many gates, which means it takes an exponential amount of time to run this program. If you want to decode the Hawking radiation at the time when you actually, in principle, can do it, I'm saying information, theoretically, you can do it, it's computationally impossible in the sense that it's exponentially hard. Because it just, the terminology in quantum information. So one possibility here is that you say, well, maybe Hawking's calculation is in some sense coarse graining over high complexity operations. If Hawking's calculation only has access to polynomially hard quantum tasks, meaning anything that's exponentially hard to compute, exponentially complex, Hawking can't compute, then he would conclude that the radiation does not contain information about the black hole interior, even after the page time. So this would have been my perspective. This was my perspective pre-2019. I would have said, okay, that's it. It's just a complexity coarse graining. Hawking's calculation is only good for polynomially bounded operations. Now, if you ask most people now, they probably would say something like, Hawking used the wrong saddle in the gravitational path integral. But of course, with the wrong saddle here corresponds to the subdominant quantum extremal surface, which is just the empty set. Now, of course, Hawking didn't use the gravitational path integral. It's also not clear where you started to just indiscriminately coarse grain over high complexity tasks. But we're trying to sort of bridge the gap between the two and have them both on the same footing. So having an understanding of where they might be different is very valuable. Now, the question is, given that we have these two perspectives on the difference between the Hawking calculation and the quantum extremal surface calculation, is, sorry, let's skip the slide here. Or did not skip. Okay, well, there should be another slide, which I'm just going to talk about. The difference between these two. So we would like to understand the difference between the Hawking calculation and the quantum extremal surface calculation. We have these two different perspectives. Is it possible that they're really one and the same thing? Is it possible that we can tie the use of the wrong saddle to coarse graining over high complexity quantum tasks? And the answer is yes. So don't let the name fool you. This is not something super silly. The Python's launch proposal. So there's a motivation from tensor networks, which I won't really go into, which proposes that whenever there is a non-minimal, a subdominant quantum extremal surface in the, forget about the entanglement, right, just inside, in between the minimal quantum extremal surface and the boundary, then the reconstruction, meaning decoding, is going to be exponentially hard. So, going to the pictures. So here we imagine, is it this here, the bifurcation surface? This is the minimal quantum extremal surface, meaning you can decode everything up to here.
How is it defined again? X-min?
X-min is this is the quantum extremal surface. This is the minimal quantum extremal surface.
But what does minimal here mean?
The minimization over the generalized entropy, smallest value of generalized entropy. So here X is non-minimal in the sense that it's a local extremum of the generalized entropy, but it has a larger generalized entropy than X-min. Now, whenever you have a situation like this proposal, which is only proven for toy models of tensor networks, but it appears to work very well, is that everything in between this and that, so this looks like kind of like a Python's lunch geometry. So everything in the lunch is exponentially hard to decode if you're sitting out here. So this would explain the connection between non-minimal quantum extremal surfaces, the subdominant ones like Hawking's quantum extremal surface after the page time, and the existence of exponentially complex operations that we have to do to decode the interior. Now, we actually have to go a little bit further, I should say, in order to, so the Python plan proposal essentially said, whenever you have one of these non-minimal ones, the construction is exponentially hard, but actually we want the other direction. We want to know that whenever reconstruction is exponentially hard, we want to have both. We want to know if and only if decoding is exponentially hard, will you have one of these? That will allow us to identify Hawking's calculation with both the non-minimal saddle and with an ignorance over high complexity operations which are necessary for the decoding of the black hole interior.
Could you just say something about what it means to decode something and why, what relevance that has to the extremal surfaces here?
Well, right. So I think you were out for a moment when I discussed that. So, okay, so this is good. So we want to merge these two calculations. We want to understand the gap between them, which means understanding in some sense where Hawking went wrong. So one way in which we can say Hawking went wrong is that he didn't understand the fact that you need to, but he wasn't sensitive to the fact that you need exponentially hard, you need to be able to execute quantum tasks that are exponentially hard in order to see that the radiation contains information about the black hole interior. So what I mean by decoding is that if you throw in a diary to the black hole and the black hole evaporates, and you want to read the contents of that diary, then you have to collect all the radiation, to put it through some quantum computer and have it read you the information that was in that diary. But then the only way to do that is to take an exponentially powerful quantum computer, since that was essentially what Harlow and Hayden showed, that this quantum computer has to be exponentially powerful in log of the dimension of the Hilbert space, which is proportional to 1/g. That's a very hard quantum task. So that's one way of thinking about Hawking's calculation, is to say that Hawking was simply not, he was coarse graining over hard quantum tasks, that his calculation means that you can't actually execute exponentially hard quantum tasks. Because if you could, then you could see that the radiation is exponentially complex, but you could see the radiation is purifying, and you could see the information coming out. But you can't do that if you don't have access to an exponentially powerful quantum computer. So maybe all Hawking's quantum computers were polynomially bounded in power. Now, the other possibility, of course, is that Hawking used the wrong saddle in the gravitational path interval. But we'd like to understand how those two are one and the same thing. So how do we do that? Well, this was the Python's lunch proposal, which essentially said that, and together with this more recent work that I did with Jack Pennington and Arvind Shabazzi-Moghadam, that non-minimal quantum extremal surfaces can be identified, it's both an if and only if. If and only if you have data which is exponentially hard to decode, will you have a non-minimal quantum extremal surface?
So I kind of, you went back and explained that stuff. I actually, that was fine for me. What I don't understand is, or what I don't know is, how do you relate complexity in this context? How do you even talk about it in this context? Why, right now you've just got a surface. You've got von Neumann entropies, you've got computations of these von Neumann entropies, you've got exact models so you can locate where they are and evaluate where they are and how they change and correspond them to the page time. What is complexity in this context? Like, what is it actually computing? Like, how do you compute complexity in this? So how do you prove something like, or how do you show something like the lunch thing?
So very important to your proposal, this is not proven. Okay, this is a conjecture. Now you can say, based on what is this conjecture being proposed? And the answer is that this conjecture is being proposed based on tensor network models. So tensor networks are a very, very useful toy model for ADS-CFT. They give you a way of doing a quantum information theoretic model of the bulked boundary map. Now in tensor networks, I guess I can sort of try to draw a tensor network here. So you can think of a tensor network as a quantum circuit that relates some information in the bulk and pushes it to the boundary using some, basically through the circuit. Now, the tensor network, so basically the idea is we have a bunch of tensors, and they sort of, relate to some, I mean, each one of these, takes some number of degrees of freedom, and it maps it to some other number of degrees of freedom. The idea being that this is a map that tells you how some operator in the bulk gets pushed, to the boundary. And I know this is not the most helpful description that I can give, but I'll just try to illustrate something here. Anyhow, the point is the following. So maybe I have the boundaries, or the asymptotic boundaries over here, and then I have the bulk over here. And I want to ask, how do I push an operator from the interior to the bulk? You can imagine having some model of a quantum circuit that sort of does it for you. Again, we think that ADS-CFT is secretly quantum information theoretic, Not so secretly, in many cases, we understand how that works. And so we can sort of try to write down models of that. Now, I mean, you can look at the Python large geometry, and you can say what kind of tensor network looks like that. Well, here's a kind of tensor network that looks like a Python large geometry. This is the minimal contour. This is the minimal quantum extremal surface. This is the non-minimal contour. This is the non-minimal quantum extremal surface. Again, this is a toy model. Now, it just so happens that for tensors, whenever you sort of have to, you try to, take some operator that sits here and try to push it this way. When you reach this constriction here that then expands again, this is precisely, you can actually prove, corresponds to exponential complexity. It's exponentially hard to push something from here all the way to here. Now, because the geometry of this is well modeled, it looks a lot like.
What makes it exponentially hard?
So the thing that makes it exponentially hard is something called post-selection. It essentially means that these lengths essentially encode the degrees of freedom in the Hilbert space, and you always want to be pushing from small to large, because that's the method that's easy to implement. The problem when you have a constriction is that you have to push from small to large back to small, and back to large, and that is something that is exponentially hard. It requires, you have to sort of scan through all the states and until you something about Grover's algorithm in order to pick eventually which one is the right one. Because if you're going from a large space to a smaller space, you have to pick exactly the right state to do it. And that's an algorithm which is exponentially complex. So this is sort of getting a little bit more into quantum information theory than I wanted to, but the basic idea is that for tensor networks, we understand very well that there's the algorithm that allows you to have this constriction, which is this non-minimal quantum extremal surface here. It results in it requires an exponentially hard algorithm. And given the relation between tensor networks and spatial slices of ADS-CFT, we expect that there's the same phenomenon works there. This is a proposal. This is not a proof. In general, complexity theory is very hard to prove things about. Even in quantum information theory, typically you can only prove bounds. But it has a good grounding in tensor networks, and typically we have not seen things having a good grounding in tensor networks being wrong in ADS-CFT. So far, it's a conjecture, but it sort of satisfied several checks at this point.
Say the conjecture again.
So the conjecture,
or the thought is that when you have this constriction, then you're doing the wrong saddle somehow.
no. So
what's the next slide again?
So this is
Oh, I
let
see.
me
Okay.
explain it here. So the conjecture is that whenever you have a non-minimal quantum extremal surface, anything that's between it and the minimal quantum extremal surface is exponentially hard to decode.
But are all circuits that are exponentially hard have this feature?
So effectively, yes.
So if you drew your diagram
So
differently,
I should take that back. You can just have circuits that are sort of exponentially long, but this thing does not have infinite volume, so it does not this what's going on here. A circuit that's sort of short, that has this feature has to have that, yes.
and when you say it's difficult to prove, what exactly do you mean?
So it's difficult to prove in ADS-CFT because our understanding of computational complexity in ADS-CFT is still in its infancy. So we have a difficult time. There are early models of how to get it from the gravitational path integral, but we're still working on understanding how to derive it from that. So so far this is a conjecture based on intuitions from the relation between quantum information theory and ADS-CFT. To prove it, we need a gravitational path integral formulation that we're still working on.
It's amazing that all these pieces like fit together. I mean,
Yeah.
like when you drew that diagram, I was taken aback. I mean, what the hell does circuits have anything to do with anything? But as you're saying, there's this quantum information theoretic viewpoint, and you can actually make sense of things or try to make sense of things in that context. It's kind of amazing to me.
Yeah, I completely agree. I mean, ADS-CFT continues to surprise in the sense of how closely tied it is to quantum information theory.
Also, when you said the thing about bounds, that's not so important, right? I mean, if I want to show, you know, I don't care about the constants. I just want to show that the complexity scales exponentially with whatever else. That's a much easier thing to, you can only prove things like, bounds. And as soon as you find something that's being exponentiated, you're in business. So it doesn't matter that the only things you can do in complexity theory are bounds, right? So you seem to be taking issue with that.
It depends on the bound. Can you bound it? Can you give it a lower bound that's sub-exponential, or can you not? Right. So the way that things typically work in complexity theory, they'll say something like, "Oh, I can show." So once you have an algorithm that's exponentially hard, you can say that's an upper bound. Nothing will be.
Oh, you're saying it's hard to get lower bounds. I see.
That's right. They're hard to get lower bounds in complexity theory. So, but one pretty amazing thing about Grover's algorithm, Grover search, which is what motivates this, is that there's a class of proofs on it on it being an actual lower bound. Now, those proofs have certain assumptions, so they may not always be true, but we expect that in general, Grover search actually is the most efficient search. So based on the number of proofs that are.
Yeah, but it's as you say, like it's notoriously difficult to come up with any lower bounds. In fact, to my knowledge, I don't know of any proof that any classical computer actually performs worse than a quantum computer. You just have bounds on the classical, computation, which are terrible, and you can show that with the quantum algorithm you get a better bound. But you don't actually have a proof that there is no good lower bound, that there is no exponential lower bound on a given classical thing.
I mean, that's right. That's what they call the quantum supremacy research direction. What they want to prove that there exists some quantum algorithms that
will definitely perform than any classical algorithm, and like obtaining low bounds is like notoriously hard.
That's right. Yeah. All right. So let me wrap up. Okay. So where are we at now? Well, we've computed the page curve. We learned a lot from computing the page curve. Sort of opened up a whole new research direction for us. And the gravitational path integral, I'll say, which has been so useful in the past, it's computed the entropy of the black hole semi-classically, even though that entropy counts quantum gravity microstates, which is kind of miraculous. So once again, it sort of knows too much. Right? We did a saddle point approximation, a semi-classical gravity approximation, yet this thing knows about the quantum gravity corrections that allow the entropy to come back down. So what's the gravitational path integral actually computing? Why does it work so much better than minus trace rho log rho using Hawking's calculation? Now to follow up on that, if we wanted to compute minus trace rho quantum gravity log rho quantum gravity, how do we do that? What is rho quantum gravity? Can we actually describe that thing in microstates of the black hole? Now, is the geometric holographic description of Hawking's mistake the non-minimal quantum extremal surface, or equivalently a coarse graining over high complexity? We know those two are the same thing, and they both look like they're Hawking's mistake. But how do we actually describe this in the language that Hawking used? How do we describe it in the language of Bogoliubov transformations and effective field theory and Hawking's transformations from square minus to square plus? And of course, there's $1 million question. If you were an observer sitting outside the black hole and you collected all the radiation and you had an exponentially powerful quantum computer that you fed it to, what do you actually see? That's, of course, the resolution of the information paradox. Then I think there was a question last time about non-ADS asymptotics. So now, if you agree that the gravitational path integral computes the partition function of quantum gravity for asymptotics that are not ADS, then you can actually do calculations and all for other asymptotics and find exactly the same type of phenomena. New quantum extremal surface gives you the page curve. Now, we don't really understand non-ADS asymptotics as well. In ADS CFT, we have a really good understanding of the partition function of quantum gravity in terms of the partition function of dual CFT. But with non-ADS asymptotics, if you're willing to buy the gravitational path integral, then in some sense, we have made progress on that front as well. Now, what about cosmology? Cosmology is hard because using Euclidean gravity for cosmology is very difficult. There has been some progress on this front. There are novel quantum extremal surfaces in the sitter and in FRW, but it's not 100% clear yet what they're doing, how seriously we should take those, given that we have neither an ADS CFT nor gravitational path integral understanding of those. So with that, I am exactly on the dot. I meant to finish 20 minutes early. So thank you for your attention.
Let's thank everyone for two wonderful talks by Netta. Netta, that was really brilliant. Thank you.
My pleasure. Any other questions?
So thank you. So far, if you look at the original Hawking calculation, can you see the second kind of re-derive the second saddle point in that calculation, or are you not there yet?
Can we
So
derive the?
Can you sort of see this?
I think the question is there a way to do the calculation where you're also doing this the other saddle point
Yes.
in an effective field theory
Oh,
way,
okay.
and then
Yeah.
you can add it up and get the right answer.
No, there isn't. That's what we're trying to work towards. Yeah, we do not know how to do that. So the thing that I did here was ask, what is Hawking's calculation in the language of quantum extremal surfaces? But the thing we really want at the end of the day is what are quantum extremal surfaces in the language of Hawking's calculation. Now, I suspect that they are not there at all in any way. And this is my hypothesis, my working hypothesis is the following, that semi-classical gravity should be thought of as an effective field theory, but effective in the parameter, but the parameter that you're interested in is actually applies to the tasks that you're allowed to perform. In other words, you can look at the space-time curvature and ask if it's okay, is this very high? You know, maybe an effective field theory breaks down. But also you can say, if I have some task that I want to execute that's going to take me an exponentially large amount of time, that's another non-perturbative quantity. It's exponential in g nu e to the g, then that's exponentially suppressed. And so you could say, I don't have the right to compute such a thing if all I have access to is semi-classical gravity. So my personal hypothesis here is that as long as you're doing calculations in semi-classical gravity and you don't have sort of oracle access to quantum gravity, you have no right to expect that any calculations that you do that are exponentially hard will give you the right answer. And so Hawking's calculation to simply compute the von Neumann entropy, that's a quantum hard task. And you can't compute the von Neumann entropy in a polynomially bounded time, which means that his answer is just, if you take this perspective, it's just rubbish, because he's using a polynomially bounded circuit to predict an answer for something that takes exponential time.
Which is why I won't be able to see the second saddle point.
Which is sorry?
Which is why I won't be able to see the second saddle point.
Yes, exactly. Yeah.
They just saw the second saddle point in semi-classical method calculation.
Well, so you say, okay, well, you use quantum extremal surfaces, you know, that took you a finite amount of time to do that. But that's what I'm calling oracle access, right? Quantum gravity gives you oracle access, and this is they tell you like, use this calculation.
Okay.
And in quantum information theory, we have all these proofs that you have oracle access. Quantum hard tasks become polynomially hard.
So.
Yeah.
Okay, got it.
Any questions on Zoom?